All right. Okay, so let's get started. Okay, so we have derived the Gilbert-Landau equations in the last class, and we have also used this equation for some trivial situation. So now let's use the same equations for some non-trivial problem to give you a feel of what all can be done with Gilbert-Landau equations. So we will take up the following examples to start with. The first example is Josephson effect. And Josephson effect through a weak link. So what a weak link means will be clear as I get along. Second one will be deriving the critical current of a thin wire. And the third problem that we will take up is a very interesting effect, which is one of the classic effects, which was yet another proof of flux quantization, and that is called Little Park's effect. Okay, so we will take them one by one. As of now, let's get started with the Josephson effect through a weak link. So what is a weak link? A weak link is, suppose I have a large superconductor like this, another large superconductor. I am not showing the end. These are large objects, millimeter size if you want. And a weak link is that I will connect these two now with a narrow constriction, and this narrow constriction has both the width as well as the length, this length and width. So length and width are both smaller and preferably much smaller than the coherence length. Okay, so this is what is called a weak link. Now, first, let me state what Josephson had derived for such a weak link. So let us first physically understand, and then we will try to derive the same things from Gibbs or Landau. What Josephson said is this: I know that inside a superconductor, of course, the Cooper pairs are phase coherent, so all the electrons will have the same quantum mechanical phase. Let's say I represent this with this axis, and this phase is θ1 here for this superconductor 1. Now similarly for superconductor 2, it will again be the same phase, and if there was no link between these two, then these two phases have no reason to be connected. So here it will be some other phase, and this angle will be θ2. Now what Josephson said is that if I have joined them through a large link, if I had just taken these superconductors and put them in contact, then of course what the situation that I would have gotten is θ1 equal to θ2. So that is what I call strong link. So if I had connected them through a strong link, then it would become one superconductor and θ1 will be equal to θ2. But if I connect them through a weak link, which is very thin and very short, then of course what is said is that θ1 need not be equal to θ2. I can have these two theta to be different, and let us take delta theta is θ1 minus θ2, and what Josephson said is that the supercurrent flowing through this weak link will be equal to some constant, which is the critical current of the junction, into sine theta, sine delta theta. So this is a very important equation, which essentially means that when you pass a current through a weak link, you induce a phase difference between the two superconductors. So as we will see, this has enormous implications later on for squids, for Josephson junction. It's used in terms of a particle in a harmonic potential that can be used for a qubit in quantum computation and so on. Now, what we will do now first, this I have just stated, we will try to derive this Josephson equation. So this is one Josephson equation. But Josephson, so this is, let's say, the first Josephson equation, and then Josephson also said another thing which is equally important. what he said is that if I apply a voltage across this weak link, if I apply a voltage, then this phase difference will no longer be stationary. So the second equation of Josephson said that d delta theta dt is equal to twice EV by H cross. Now, this is the second Josephson equation. And if you look at this equation in conjunction, you will immediately see something very interesting. If I apply a voltage, then delta theta will be time dependent. Suppose I have applied a constant voltage, then delta theta will linearly increase with time. But if here this current depends on sine theta, sine delta theta, so if delta theta linearly increases with time, that means this supercurrent will be AC. It will be a high frequency supercurrent. So by applying a DC voltage, you can induce a high frequency supercurrent. Your applied voltage is DC, but the supercurrent generated is AC. So this all sounds very mysterious. So now we will go ahead and try to unravel these equations step by step. Remember that a bit of historical point here. Brian Josephson was a student in Cambridge around 23, 24 years old. And at that time, Phil Anderson came to give a series of lectures on superconductivity. Brian Josephson was attending that lecture. And when he attending that lecture, he got the idea of this Josephson effect. So he wrote it up, he wrote a paper. He showed it to Anderson. Anderson was not entirely sure whether it's right or wrong, but he thought it's interesting enough. So he told Josephson to publish it. Josephson published it in Physics Letters, and that is the work that got him a Nobel Prize, I think around the age of 26. What's even more interesting is that that's roughly the only physics that Josephson did through his entire life. So he remained, later he became a professor in Cambridge. He remained in Cambridge for his entire life. But after this work, he got interested in telepathy, in homeopathy, in quantum mind-body connection, everything that is not considered as science by mainstream scientists. Josephson started being an advocate of all of these, and he never did any more mainstream science in his entire life. Okay. So let's now go ahead and in fact there is a interesting thing is the reason why Brian Josephson got interested in Josephson effect, which is essentially a quantum interference phenomena. This I don't have any documentary evidence, but I am told that his actual interest was that this might have some connection with telepathy. So he thought this as a route towards telepathy. Now this of course is an anecdote. I am not sure that's right, but whatever else I have told you is roughly correct. All right.
Hello, sir.
So, yeah.
So what will be, if I apply a AC voltage across this uh, junction, so what will happen at that time?
Okay. If you apply a AC voltage, If you apply AC voltage, lots of complicated things will happen. You will get, okay, we'll do that in due course of time. If you apply a AC voltage on a Josephson junction, what you get is something called Shapiro steps. So that's also a very interesting phenomena, but we will see. Let's first derive the basic equation. We cannot jump steps and go ahead. We will go one by one. Okay, so let us now first try to derive this. I know Ginzburg-Landau equation, and since this weak link is narrow, I can use the one-dimensional Ginzburg-Landau equation. So therefore, you know by now that the one-dimensional Ginzburg-Landau equation in terms of the normalized order parameter, oops, let me just check which form had I derived in the last class. Oh yeah, that I have derived this form. Okay, I know that this is my linearized Ginzburg-Landau equation. If I don't have a magnetic field, and this is nothing but the Ginzburg-Landau order parameter divided by the Ginzburg-Landau order parameter for a uniform superconductor, which is psi 0. Now, I will solve it for the weak link, which I am drawing here again. For convenience, this is my weak link. This point is x equal to 0 on one end of the weak link. This point is x equal to L, the other end of the weak link. And I know that inside here, this has to be 1 because these are large superconductors. So inside either superconductor 1 or superconductor 2, I will have this normalized order parameter, which is 1. Now I can take the phase. Here I have, of course, the amplitude, and I also have the phase. Let me take the phase to be 0. Okay. Now 0 doesn't mean anything. I can just take whatever origin of I can take any reference axis. So therefore, I can define my 0. But now having defined the 0, I cannot define both of them. So at the other end, let me call this delta theta. This is at x equal to L. So this is the phase of the superconductor 1 and this is the phase of superconductor 2. The difference between them is delta theta. As I have told you already that psi Italy could be 1 at x equal to 0 and psi Italy at x equal to L, what will it be? Someone tell me, what would psi italic be at x equal to L?
C to the power I delta theta.
Tell me again.
E to the power I delta theta.
Exactly. Perfect. E to the power I delta theta. All right. Now we have to make some approximations. And that approximation will actually make it quite trivial, but does not matter. So the approximation is the following. Before I go with the approximation, let me myself recall what the approximation was. Okay. So now let me look at the relative terms here. So I will look at the relative weight of these terms and see if I can simplify further. So let me take these terms, psi square, psi mod square, d square psi dx square. Now this will be roughly of the order of psi square remains psi square. This quantity will be roughly of the order of delta theta by L whole square. So I am just doing order of magnitude estimate, which will be of this order. Now remember that I have assumed the weak link, the width and length, to be much smaller than the coherence length. So therefore xi by L whole square is a large quantity. On the other hand, for the second and third term, there is nothing which is amplifying. So therefore, this term will be much larger than the remaining two terms. So I
Sir,
will
can you explain this once again?
see this is a large quantity.
Oh, okay. Yeah.
Okay, because I have assumed that L is much smaller than xi. All right. So therefore, there is an amplification factor here. There is no amplification factor in the remaining two terms. So therefore, I will just drop the two terms here and just keep this as my solution. So now this becomes trivial. The solution consistent with the boundary condition. It's very easy to solve it. I will just write the answer. Is this plus okay. So you just see x equal to 0, it is 1. X equals to L. X equal to L, it becomes 0 and it becomes e to the power I theta. So this is the solution that I have, and I can write it in the form 1 minus x by n into good. So now the rest is trivial, because the rest what I have to do is to calculate the j. And I know that j is e to the power, sorry, it is eh cross by twice mi. Should it be E star or should it be E? I forgot. Does anyone remember? I think it should be E star. And then I will have psi star grad psi minus psi grad psi star. Now this is not in italic, so I will have to, when I take the italic out, I have to multiply it. So let me, grad psi would be minus 1 by L. Here I will have to put the psi 0 and then 1 minus e to the power I delta theta and psi star, of course, will be 1 minus x by L, and here I have E minus delta theta. All right. So this quantity, of course, you know that I don't need to evaluate both the terms because this is just twice I imaginary of psi star grad psi. So therefore, what I will get twice of imaginary psi star grad psi will be twice psi naught square by L into sine delta theta. So therefore, now my supercurrent J okay. So we have already proved by now that the supercurrent is proportional to sine of delta theta. This is what we had set out to show, but let us get it into slightly better form. E H cross. Now psi 0 square is of course ns. So let me put ns there. Then ml okay. So this immediately tells you that this quantity is the maximum current that you can flow through such a weak link, and this is the critical current of the junction of the weak link, if you want. What we will do in the next class, when we do the critical current of a thin wire, which is, let's say, the wire of the same diameter, or the width is the same, but then the length is very long, you will see that the critical current of this wire, if I call it ICW, this ICW, this is larger than ICW. And the reason why this is larger than a wire of the same width as the link is because these two large body of superconductor, these two reservoirs, they provide a rigidity on, they provide a robustness on the link itself. Okay, but that's for the next class. In this class now, we have derived the first Josephson equation. So you have the first Josephson equation and you have shown that J is proportional to sine delta theta. Remember, I should write strictly Js because this is the supercurrent. There are situations where I can also flow along with the supercurrent, I can flow a normal current. But that I am not considering here. The normal current I will be flowing when I apply a voltage. But up to a current of IC, or actually, I'm sorry, this should not be IC, this should be JC. I have to multiply by a numerical factor. I have to multiply by the cross section in order to get IC. Okay, so up to this critical current density JC in the link, I will not be producing any voltage because I am only passing here a supercurrent. Now let's go and derive the second equation. And derivation of the second equation is extremely instructive. So first let us remember what was the second equation. The second equation was this one. Del d of del theta dt is twice EV by H cross. V is the voltage applied on the junction. So when I am applying a voltage on the junction, then delta theta does not remain a constant. It becomes a time dependent function. Okay, now this goes into the heart of superconductivity, and it will essentially go to the fact that a superconductor breaks the gauge symmetry. So we know that you have the Maxwell's equation, which I can write in terms of vector and scalar potential. So this is the magnetic field and the electric field is minus a gradient of V minus 1 by C del A del T. You have all studied this. Now you know that in electrodynamics we have something which is called gauge invariance. What does gauge invariance tell me? Gauge invariance tells me that if I replace A by A plus the grad of a scalar quantity. I can call this A prime. Then if I replace at the same time V by V minus 1 by C into the time derivative of the same scalar quantity, my physical equations will remain the same. So instead of using a pair of potential which is A, B, A means it's a vector, so it has AX, AY, AZ. So AX, AY, AZ and V. I can replace everywhere these with A prime and B prime, and no physical quantity would change under such a transformation. So gauge invariance is of course fundamental in electromagnetism, but when you try to deal with a superconductor, we run into a difficulty. To understand what is the difficulty we run into, let us first calculate the expression of the current. So we did it, but we will do it again. And when we do it, there is something that there is an assumption that we will do. Okay, now if you remember in the last class, I have shown you the Mexican hat potential, and that is how the Green-Zurlanda of free energy looks like. So remember, in the Green-Zurlanda of free energy, you can change the phase of a superconductor by not changing the energy at all, because your minima lies actually on a rim. So therefore, you can change the phase of a superconductor, and as long as you bother to change the phase of all the Cooper pairs in the superconductor, nothing would change. Energetically, it is just the equivalent of taking this magnet and rotating and pointing in another direction. So there is no energy cost of doing that. However, if you want to change the amplitude, then that is exactly the Higgs mode that I was explaining in the last class. So if you want to change the amplitude, you have to change the amplitude of psi, and changing the amplitude of psi, that is a mode that costs you energy, because you have, do you all recall the Mexican hat potential that I showed in the last class? Otherwise, I will show you again, because whatever I am saying will not make sense. Well, I don't hear a yes or a no. What do I make out? Do you recall or don't you recall? Okay. I am not certain, but let me go ahead assuming that you recall. So therefore, it is energetically much more favorable to change the phase of the wave, to change the amplitude of the, sorry, it is energetically favorable to twist the phase of the order parameter than to we put a gradient on the amplitude. So therefore, what we will assume here, we will assume that for a bulk superconductor, I have the amplitude that is not a strong function of R, but theta is a function of R. And that's a realistic situation if you take any bulk superconductor. When you go to superconducting nanoparticles and so on, things become different. But that is something that we will deal later on, and the group that is doing the video project on nanoparticles will have to deal with it in very great detail. But as far as the bulk superconductor is concerned, it is practically very legitimate to take the order parameter of this kind. So therefore, what I get here is E star by M star. This is J. Chi mod square, and then here, actually I can even take the H cross outside. I think that would help. All right. So this is my expression for J, and J is current. It's a physical quantity. There is no way that J can depend on which gauge I am working in. So this has to be gauge independent. There is no way that this can depend on gauge. How can this be gauge independent if it depends on A? There is only one way it can be gauge independent. And that is, if when I am doing a gauge transformation, I also do a transformation of theta. So this is the fundamental thing where this is the fundamental symmetry that a superconductor is breaking. When I am doing a gauge transformation for a magnet, I don't have to rotate the magnet. So the physical phenomena will remain the same in whichever gauge I use. If I take a permanent ferromagnet here. But if I take a superconductor, whenever I am changing the gauge, I have to simultaneously change theta, otherwise my physical quantity J will come out to be different. So let us see how you have to change it. When you do a gauge transformation, A goes to A plus this gradient of some kind, which means that theta will have to go to theta plus E star by H cross C into that same kind is also a function of t. So if I am using A prime, I have to also use theta prime. Now I remember that I had an equation for V that I have written earlier. which was, this is the equation for V when I do a gauge transformation. So therefore, from this equation, I will just multiply E cross E by sorry E star by H cross. So then I will have, what do I have here? Wait a minute. E cross B minus E star B by H cross minus E star by H cross C into d chi dt, and this I will write it as V prime E star by H cross. This quantity I will take also a derivative of a time derivative of both sides. Let me see if I have the derivation here. Yeah. Okay, d theta dt. So I am just taking this equation here and doing a time derivative on both sides. Excellent. So now I have these two equations. And I can add both sides. So what will I get is d theta dt plus E star V by H cross equal to d theta prime dt plus E star V prime by H cross, which means that d of delta theta, theta minus theta prime is what I am calling delta theta, equals to, here now remember E, okay, first then let me not jump steps. Delta V is V minus V prime equal to 0. Now the charge of E is E star is negative, so I put a modulus and that is why I get the negative sign here. Now you know that H by E star is 2E. This is my flux quantum. Alright? So therefore from this I will get delta V, which is and this is my second Josephson equation. All right. So this is the basic phenomena of the Josephson equation is encapsulated in these two equations. Now, in the next class, what we will do first is to do the critical current of the wire and then the little parts effect, as I mentioned, and then we will come back to these Josephson junctions and we will take a realistic Josephson junction and see how their current voltage characteristics behave. If I measure I as a function of V, current as a function of voltage, or voltage as a function of current, whichever way you want to do your experiment, what will I get there? Now, one of the things that I want you to note here, this I have circulated just before the class, I have circulated the assignment problems, and this is the third assignment problem. The third assignment problem is when we derive the first Josephson equation here, we have assumed no magnetic field and we have gotten J to be proportional to delta theta. But just now I showed you that just like that theta in itself is not gauge invariant. What is gauge invariant is a quantity that has theta and A both. So I cannot just write in terms of theta, because if I go to another, if I do a gauge transformation, this will not work anymore. So that means that this equation is valid only for A equal to 0, that means no magnetic field. What I want you to derive in the homework problem is the corresponding equation that you will get in the presence of a magnetic field. Now, what you will get in the presence of a magnetic field is very interesting. You will get the supercurrent will be again the critical current, sine of a slightly different phase, which we call the gauge invariant phase. Now, what is gauge invariant phase? The gauge invariant phase is actually this quantity here. It has, of course, the regular delta theta, but then it also incorporates A inside. So, if you want this line integral, it extends from x equal to 0 to x equal to L. So, what you have to do is that when we started with our equation of our linearized Ginzburg-Landau equation, we took this, and here explicitly the vector potential was missing. What you have to do is to rederive this equation, the supercurrent through the junction, but now incorporating the magnetic field. And you have to show that what will come here in the presence of a magnetic field is this gauge invariant phase. So this is what is called the gauge invariant phase. All right, so let's stop here and questions.
Sir,
Yeah,
sir, the delta theta that you have written in the last case is theta prime minus theta. This theta prime is appearing due to the gauge transformation, right?
yeah,
Yeah, but the theta, the theta that you have defined earlier, that is the phase difference between the two parts of the superconductors. There is no.
exactly. So the point is that, see, there is no meaning of a voltage at a point. The voltage is always across something.
Yeah,
Okay, so voltage always, what this tells you is that this quantity V means this quantity will always be zero, which means that why did I have that? Let me see what is the equation. Yeah. Which means that V1 equal to phi naught by 2 pi d theta 1 dt. This is one end.
yeah,
You
yeah.
remember theta 1 and theta 2. And then V2 on the other superconductor will also be the same, will also follow the same equation in the corresponding theta. Now, V1 minus V2 is your V, and theta 1 minus theta 2 is your delta theta. What this equation is telling you is that this is a gauge invariant expression which will always be valid. So it's valid at one end of the Josephson junction, it's valid at the other end of the Josephson junction.
Okay, sir. Okay, okay. Good.
Okay.
Sir, one request, sir, that we have an exam, we have StatMech exam in the Sunday, in the coming Sunday. So, and the deadline is in the Saturday.
This assignment is so easy that don't ask for an extension of deadline. This is just a warm-up assignment. It's actually child's play. If you are following the lectures, then this will take you 15 minutes to do it.
Okay, sir.
All right. Any other question? If not, we'll meet again on Wednesday.